So here we have a cost function from economics, and when we have the derivative and the derivative of the cost function, well, that's going to be what we call the marginal cost at the margin. And it gives us the marginal cost when production equals x, whatever x is. X is the placeholder here. Whatever value x is, it tells us the marginal cost, and I'll explain exactly what it means a little bit later in this video. Now, if h is very, very close to 0, but not equal to 0, this thing here is just going to be equal to cx plus h minus c of x over h. Now, the numerator, this is the incremental cost of producing h additional units of output. Now notice that h can be less than 0. Well, can be. It doesn't have to be. But h can be less than 0. So if we reduce output, we can think of cost savings, right? If we don't try to make as much stuff, we can save some money. Of course, it still has to be the case that the overall marginal cost is greater than 0. We can't start having negative costs here. Now this, let me take this and move it over here. This is approximately equal to, and I'm going to erase the denominator because this thing, the numerator there, is approximately equal to h times c prime x. So if we take the marginal cost and multiply it by the additional units, this is going to be equal to, or excuse me, approximately equal to the incremental cost of producing h additional units. So I'm trying to be very specific here, very clear, because I want you to understand, try and understand exactly how the calculus relates to sort of those business topics, the regular economics topics that we talk about when we talk about the margin and units of production. So we can say that the marginal cost C prime x is approximately equal to, oh, I'm running out of space, the incremental cost, where the incremental cost is this thing here. Now you might ask yourself, what on earth is a linear approximation? Well, I mentioned it on the previous slide. I'm going to take a minute to try and explain it to you because you're going to need to know this, especially in Chapter 7, when we're looking specifically at functions where we need to use linear approximations. So on the previous slide, we said that just taking the marginal cost, that instantaneous rate of change, and multiplying it by h, that gives you an approximation of the incremental cost. Now, what does this look like on a diagram? So I'll try and sketch it out for you. Keep in mind that you are going to have to learn this later in the course, and maybe I'll draw a curve like that. Okay, this curve is much better. Now, suppose I'm interested in what's going on here. We'll just call that, well, let's call it A. We've got X here, we've got Y here, and we know that the Y value is some function of A. Now, I'm going to use the tangent, so I can draw the tangent. We've got a tangency point right here at A. So this is the tangent line for f of A, and the slope of tangent line is f prime A. Right. If I want a linear approximation is, well, it's like using the tangent line to estimate values of f of A plus h. Well, let's use a number, say f of A2. So say I want, and we'll say f of A minus 2. So suppose I wanted to know what A plus 2 and A minus 2. So I'm going to draw the curve down there. Now, I could use the tangent line here. It's like saying, well, I've got f of A plus h times f prime of A. So I'm using the slope of the tangent line to predict what the value of y is going to be. And then down here, it's like writing f of A minus 2 times the slope of the tangent line. And that's what we meant on the previous slide when we had h times c prime A. Well, I guess it was actually x, so I'll write down the x. So sometimes we refer to linear approximations as walking along the tangent line. So now, I'm not going to try and explain to you why. Why would we use a tangent line? Why don't we just actually directly solve for the function? I'm not going to explain why exactly that is. I'll just say that in some situations we can't do that, or it's extremely hard to do, and so we use linear approximations. We'll cover that in Chapter 7. We'll go into more detail. For now, I wanted to introduce this to you because it's very, very important, and students struggle with it. Mechanically, it's really easy and straightforward. The intuition, the concept, is a little more challenging. Now, what happens if we let h be equal to 1? Well, looking over here, we don't even really need to use the limits. We're going to have the cost of production when we're producing x plus 1 unit minus the cost of production when we're producing x units, and it's going to be divided by 1. And our marginal cost, that instantaneous rate of change, oh, and I don't want to draw equal signs, is going to be approximately equal to C, the total cost of producing X plus 1 units minus the cost of producing X1. And what is that? Well, in some textbooks, introductory economics textbooks, that's your definition of marginal cost, and that's where it's coming from. So instead of letting H be really, really, really close to 0, really super small, we've allowed H just to be equal to 1, and then we've come up with this calculation for the marginal cost. All right, let's apply what we've learned. We've got a cost function here, and the cost function is the cost of removing a % of pollution from a lake. And the total cost function is C of X, where X is a percentage. And it hasn't been defined for us. But we know that the marginal cost when X is equal to 50% is $3 million. Okay. So how would we interpret this? Well, I would say, given that 50% of the pollution has already been removed, the cost of removing 1% of the pollution is $3 million. Maybe another way to look at it, since it's a cost function, given that you pay to remove 50% of the pollution, the cost of removing 1% of the pollution more, or maybe 1% more, is $3 million. Now, where does the derivative appear in economics? Well, you already saw one example. If we're looking at a cost function, if we're looking at the cost of a firm and we have an equation that expresses it, the derivative of the cost function gives us the marginal cost. If we're looking at profit, an equation that expresses the profit of a firm, the derivative of that equation, the derivative of the profit, is the marginal profit. This is the concept of marginalism. And what it does is it tries to explain the value of goods and services by reference to their marginal utility. And my personal favorite economics blog, Marginal Revolution, it says right there, it's the most popular economics website on the internet, and it's called Marginal Revolution. And I'm going to give it a pitch here. Their motto is small steps to a much better world. And that's a lot of what economists do. By looking at the margin, these very tiny changes, decisions we say are often made at the margin. And if you can make little small changes to these decisions for the better, you can make a better world. And that's a lot of what economics is today, looking at the margin, looking at these marginal costs, looking at these marginal profits, because it actually does quite a good job of explaining human behavior. And if you're interested in economics, you want to learn more about economics, I highly recommend their website. Now, let's look at an application of the margin. So what is all this marginal mumbo jumbo? It actually goes back, marginal analysis goes back well over 100 years. Now, the question that perplexed Adam Smith was, why do diamonds cost so much more than clean water? Clearly, clean water is more valuable to us than diamonds, right? If you don't have water for 1 or 2 days, you're probably going to be willing to trade me, quite a few diamonds in exchange for water, right? Going thirsty becomes very, very painful. And so on that note, shouldn't water be more expensive? So think about it for a second. Now, economics is all about scarcity. So if you're starting to think about scarcity, you're on the right track. But it's a very particular kind of scarcity that's going to lead you to the right answer. Diamonds are more expensive than water because the marginal benefit you enjoy from having one more diamond is greater than having one more glass of clean water. If you're living in Toronto and you have a decent apartment and a decent house, and you're not in poverty or something really, and even then, if you're in some very unusual circumstance, you have lots of clean water, right? I have lots of clean water. All I have to do is turn on my tap, and I have access to clean water. So one additional glass of clean water doesn't have much value to me. I already have so much. But I don't have very many diamonds. And so I'd be willing to trade a lot of my many glasses of water for diamonds because I just have so much water. I really just have so much, and I have more than enough that I need. And so I place value on the thing that I don't have. Now, if I'm on a desert island, or if I have to choose between diamonds or water, I'm going to take water every time. But given where I am right now, I've got plenty of water. I would definitely trade some of my tap water for some diamonds. And that's what we mean when we talk about marginalism and thinking of things at the margin. At the margin, I'd like a little more diamond and a little less water, partly because I have so much water. I recommend you try this problem. See if you can remember the Newton quotient. We've got a profit function here, and we're being asked to calculate the marginal profit. And then I want you to tell me what would we call the marginal profit in calculus language. All right, so I'm going to write out my Newton quotient. I've got the limit as h approaches 0 of negative q plus h squared plus 24 q plus h minus 5. And this whole thing is going to be minus q squared. Should have another minus in front of that. Plus 24q minus 5. And this whole thing is going to be divided by h. Now I'll rewrite my limit. And notice I've got the negative exponent on the outside. So I'm going to have q squared plus 2h plus h squared plus 24q plus 24h minus 5 plus q squared minus 24q plus 5. and this whole thing divided by h. Rewrite my limit. And we've got, well, I can see that my negative q is going to go away. I've got, what have I got here? Jeez, I've oh, no, I was right. 2qh, just like that. So I'll leave negative 2qh minus h squared plus 24h, 5s are gone, and this whole thing is divided by h. Now I can see that I'm going to have an h there and there and there, and they're going to eliminate each other. I'm going to keep my limit, negative 2q minus h plus 24. And if I actually take the limit of this, I'm going to let h be equal to 0. And then I'm going to have negative 2q plus 24. And this is my marginal profit. So if I want to find the slope of a tangent line at a specific point, I want to find the marginal profit, right, which would be equivalent to finding the marginal profit at a given point, then I now have a function that'll let me do that. And this is called the instantaneous rate of change. Instantaneous rate of change. I guess I've solved the problem. If I wanted to find the max of this problem, or the min, notice that we've got a max because we've got negative q squared plus 24q minus 5. And I know that if q is equal to negative b over 2a, and I've got b is equal to 24, I've got a is equal to negative 1, then I'm going to have 24 over negative 2, and q is going to be maximized when it's equal to 12. Seems reasonable.